In this class, we want to build upon what we've been looking at in recent videos, which was the idea of the limit of a function and continuity, to define one of the two main operations in calculus, which is differentiation. So calculus is split differentiation and integration, and in calculus 1 in this course we're looking at differentiation, and in calculus 2 we look at integration. If you've not been watching the videos in this series, I would encourage you in particular to watch the last couple of videos where we really looked at, in particular, the tangent line problem. So this is really the problem that started calculus, several hundred years ago. Mathematicians were kind of grappling with the idea of how to define, in particular, the slope of the tangent line to a curve. So we introduced 2 videos ago the idea of just putting another point on the curve and constructing a little line between these 2 points and realizing that that dashed line there is an approximation for the gradient of the line of tangency. But it's not the line of tangency, it's an approximation. But we realized then that we could start to shrink that second point back towards the point of tangency, and as you do that, your tangent line gets closer, or maybe the other way to put it, the dashed line gets closer in gradient in slope to the tangent line. And if you shrink it all the way back, then you actually get exactly the slope of the tangent line. And that's what we covered in 2 classes ago as an approximation, and in the previous class we introduced the idea of a limit. So we basically built the limit definition of the slope of a tangent line by saying that if we shrink this all back shrink these points back to the point of tangency, we need to use the idea of a limit to do so. So we introduced the mechanism of a limit to help with that shrinking back process. But effectively this was just built out of using 2 points to make the gradient, the slope, then introducing the limit to shrink that back to 0. So what we want to do now is to generalize that idea to define in general terms what is called the derivative of a function. So we basically had already in the previous class defined the derivative, but we didn't call it the derivative at that point. We just called it we called it the limit definition of the tangent line slope. And we just used it as a tool to help us get the gradient of this function, or the gradient of the tangent line at that point where it meets the function. But now we're going to define the derivative. So in this previous way of considering things, we said that we could start off by taking, so if this was our function f, we said that if we take f of, the way we conceived of it was x plus delta x, so f of x plus delta x. And if you're not sure about the delta x, then you have to watch the previous videos. I'm not going to go through it again in this class because we want to move on a little. So f of x plus delta x minus f of x divided by delta x. And that was basically just using the formula for a gradient, and that gave us this kind of dashed line here as gradient. But then to refine that, we shrunk it back to 0. We shrunk the points back towards the point of tangency using the limit. So we took the limit as delta x tended to 0 of this quantity, and we called that our way of basically getting the slope of the tangent line. And that's perfect. That is the slope of the tangent line. But what we're now doing is we're now saying this actually represents what we're calling the derivative of f. Okay, so the derivative of the function f at the point x. Okay, and we're going to notate that as f prime of x. So f prime of x is equal exactly to this limit, where the limit exists. And there's some functions which you'll see for which the limit does not exist. So those functions do not have a derivative. They're not differentiable. And we're going to deal with the idea of differentiability in the next class. Here we're just defining the derivative. So this is exactly how you define the derivative of a function, this little formula here. Or this is in general terms for any x value. If you want to define the derivative at some particular point, so at the point where x is equal to c, then we take the limit as x tends towards that point c of f of x minus f of c divided by x minus c. And this is just exactly the same thing. It's just that we're dealing with a particular point along the curve, a particular point in the function, not just in the general case up here. So that is how you define the derivative. Now, when it comes to actually taking derivatives, which is what largely the rest of this course is about, you're not actually going to use this definition very often. If you took a derivative of a function using this definition here, we would call that taking the derivative from first principles, and your teacher might ask you to do that. It is an important skill to be able to do, but it's a very long process, and we now have tools and techniques and like mechanisms to not have to do that. We can take derivatives very quickly using a whole bunch of techniques that you're going to learn in classes further on in this series. So it's important that we work some questions like this to know where we have got all of those more efficient tools from, but in reality we're not usually going to use this definition very much, although you should, absolutely should know this definition. So what we're going to do now is we're going to go ahead and work an example here, this function here, to find the derivative of this function using this first principle definition. Now just to put out there now, if you're given a function in terms of f, so if f is how the function is defined rather than y, because remember sometimes functions are defined as y equals, in particular when you're referring to the graph of the function, if it's defined as f, then the notation for the derivative is f prime of x. Okay, like this, that's how we notate the derivative, or it's sometimes called f dash x, but f prime of x, f dash x are basically what is happening there. If the function is given as y, then the derivative is notated dy dx, okay? And the d is basically the delta, so it's delta, oops, that should be a y, not an x, so it's delta y over delta x, which basically is just, again, fitting in with these definitions here. Now, why are there two notations? It's because historically, two different mathematicians were working on this problem independently. They thought about it in slightly different ways. They conceptualized it in different ways. We've ended up therefore with two different notations. They kind of mean different things, but they give you the same result. So it doesn't matter which method you use. Well, in reality, you'll only be using the techniques you're going to learn later in this course anyway. It doesn't matter which notation you use, you should get the same result. Right, so we're going to try and find our derivative here. So f prime of x. So we know using this definition here, we can find that derivative. So it's going to be the limit as this delta x tends towards 0. And again, if you're not sure about this here, where this has come from, I really encourage you to watch the previous two videos so you can build your knowledge up to this point. So it's going to be the limit as delta x tends to 0 of this thing here. So we're going to take x plus delta x and put it into the function. That just really means replacing all of the x's with x plus delta x. So we get x plus delta x squared plus 3 times x plus delta x. Okay, so that would be this part here, and we're subtracting from that, and I'll maybe just use a bracket, f of x. So f of x, which is, I don't need an f in there, sorry. So we're just subtracting f of x, which is just going to be x squared plus 3x, okay, like that, all of that over delta x. And we're just going to work with the algebra a little to tidy it up. So limit as delta x tends to 0. This here is a bracket squared. You would need to write that bracket twice and think of how you'd multiply that out, maybe using a technique like FOIL, but essentially that's going to come out to be an x squared, and then you're going to get 2x delta x plus delta x all squared. So if you're not sure what I did there, just take your time, write that bracket down twice, and then multiply it out. I know it's a bit weird working with that delta x. It's a weird looking little, kind of thing. You're probably not used to doing that, but it just works like normal bracket expansion. So multiplying the second bracket out, we get 3x minus 3 delta x. Multiplying this minus 1, if you like, or expanding the bracket with the minus, we're going to get a minus x squared and then a minus 3x like that. And all of that over delta x. Now, the way that these always work is that terms will cancel. So here we've got an x squared, and here we've got a minus x squared, so they're going to disappear. Here we've got a 3x, here we've got a minus 3x. They're going to disappear. If you don't get that cancellation, then something's probably gone wrong. So look out for that if you're doing questions of this type. So this comes down to the limit as delta x tends to 0 of 2x delta x. I'm just writing out what we've got left over, plus delta x all squared minus 3 times delta x divided by delta x. So notice that everything has now got a delta x in it, so we can do some further cancellation. And I'll just take a line to write this out to make it clear. Dividing everything by delta x. If you divide this term by delta x, you're going to get a 2x. If you divide that term by delta x, you'll just power down to a single delta x. Divide this by delta x, and you're going to get just minus 3. The denominator divides down to just 1, so we don't need to write the fraction anymore. We're basically left with this quantity. Now, if you've been watching all the videos in this series, you'll know that you can evaluate this just by direct substitution. If we put a 0 in here for delta x, we're not going to get what's called an indeterminate form, and you'll know what that means if you've been watching these videos, so there's no problem with doing direct substitution. So effectively, the delta x tends to 0, goes to 0, we can sub in 0, and we just get the final answer as 2x minus 3. So that there, 2x minus 3, is our derivative, is the derivative of the function f prime of x. Now that is by first principles, and notice it's quite a long algebraic process. There's a fair bit of scope for making a mistake in here, and students, often do, especially with having this weird delta x kind of term kicking about. In truth though, the reality is that when you learn the rules for differentiation, you're going to use something called the power rule on this one. If I was doing this by the power rule, I would go like this. F prime of x equals, and that rule tells you to take the 2 in front, so you go 2x, and well, you'll see the rule when you get there, but basically the 3x becomes just a 3. So, I've actually ended up with the wrong term here. How did I do that? That's because that was meant to be a plus. Awful mistake there. That should have been a plus, so it should have been 2x plus 3. So basically, if you're differentiating this using the rules you're going to learn in this series, you will learn to differentiate that function within, well, how long did it take me to write that down? Like 5 seconds maybe? How long did this take me? Like 2 minutes? So the truth is that we don't do differentiation by first principles unless you're being asked to do that specifically to test your knowledge on how this little formula works. We would just, this would be pretty much the most simple differentiation case you could get. You will directly learn to write that down, and that will be your derivative. We get the same result by first principles, but it's a much more long-winded process. So it's really important that you learn these formulas, and it's really important that you can do this technique. But as you move forward in this series, this is going to get backgrounded. This technique, this mechanism, this kind of the mechanics of what I've done there is built into the rule that I've used to go from there to there, but it just gets backgrounded. You don't need to think about this. There's a more direct way of getting straight to the actual result, and you're basically going to learn a whole bunch of rules, maybe up to sort of 10 rules or something like that in the rest of this course, where you're going to take functions that are of different types, different forms. This is a polynomial type function. You're going to learn about rational functions, composite functions, trigonometric functions, all sorts, and you're going to learn different rules that will allow you to go from there to there, generally very quickly. Sometimes they need a little work, but generally very quickly, certainly a lot more quickly than using first principles. But this is just part of the journey you've got to go through to learn basically how calculus gets built up from first principles to the rules. So this class is essentially been about defining the derivative. So we've just basically extended this idea of the tangent line problem, figuring out the slope of that tangent line. We've extended that or generalized that to this definition of what we've called the derivative of a function at a point x or at a point c. And going forward with the rest of this course, you're just now going to learn different techniques as to how to efficiently take the derivative, find the derivative of a function where it exists. And they don't always exist. For most functions you'll work with, they do exist. If they don't exist, it's because the limit of this quantity here cannot be taken. If the limit doesn't exist, then the derivative does not exist either. So I'd encourage you to spend a little time making sure that this is clear. Once it is clear, you can start to get on with the process of learning all the rules. In the next class, we're going to talk about differentiability. So we're going to consider the idea of when a function is differentiable, when it's not differentiable, which is a big decision you always have to make when you're doing derivatives. Is the function differentiable? If I'm trying to differentiate it, but it can't be differentiated, then obviously you've run into some kind of problem. So hopefully that makes sense, and then we're going to deal with differentiability in the next class. So scoot on over there when you're ready.